Hey everyone, welcome back to the Foundry by Forge College. Alright, so let's pivot. We are stepping away from our previous lesson on memory efficiency techniques in C-level, and we're heading right back over to the Ethereum ecosystem. Today, we're going to fix a major glitch in your testing machine. We are right in the thick of the Hardhat Fundamentals course, specifically focusing on testing smart contracts with Hardhat, which is all part of the broader Ethereum DevStacks and Frameworks track. Okay, here's the game plan for this explainer. First, we'll unravel a flaky test mystery, then look at awaiting the final receipt and mastering Mocha test hooks. After that, we'll build a predictable test pattern, talk about handling expected reverts, and finally, hand you your testing blueprint. Let's get right into it.
Section 1. The Flaky Test Mystery.
Man, we have absolutely all been there. You've got a test, it passes perfectly on Tuesday, and then suddenly out of nowhere it fails on Wednesday, and you haven't changed a single line of code. You run it again, it passes. Run it a third time, it fails. You honestly start to think your computer is haunted, right? Well, there are no ghosts here, just asynchronous operations. See, this glitch happens because async contract interactions are basically like non-deterministic moving parts on a factory floor. If Mocha, that's your testing framework, finishes its job before the blockchain operation finishes its job, well, your test assertions end up running against a totally incomplete half-finished state. And that brings us to the real villain of the story, the unhandled promise rejection. This happens when an async operation fails, but the test framework doesn't explicitly catch or await the error. It is the absolute enemy of a smooth-running machine, causing unpredictable timing and, worst of all, false results. Fixing this means we really need to understand the life cycle of JavaScript promises and Hardhat's transaction behavior. Basically, we have to tell our tests exactly when to wait. Which brings us to Section 2, awaiting the final receipt. To fix our machine's timing glitch, we need to introduce the primary mechanical parts here. We're talking about promises, the await keyword, and the absolutely critical difference between a submission and a confirmation. Think of it like this. Calling a smart contract is a lot like placing an order at a restaurant. A transaction response, the submission, is really just the way to writing down your order. It's a promise that you'll get food, but asserting your contract state right at that exact moment without waiting for the transaction to actually be mined is like trying to eat the receipt before your meal even arrives. You're going to have a bad time, and your test is definitely going to fail. So the magic words here are await tx.wait. You have to explicitly sequence your tests to await both the initial submission of the transaction and the final confirmation receipt. Now, I know Hardhat gives you this local, in-memory network that mines transactions incredibly fast, but it still has those two very distinct stages. Awaiting the tx.wait guarantees you are looking at actual finalized on-chain changes before you run your checks. Moving right along to Section 3, Mastering Mocha Test Hooks. Okay, now that we have our await parts, let's map out the assembly line protocols. We've got 4 main hooks in Mocha: before each, and after. The most crucial detail here is the async usage. By using the async keyword on these hooks, Mocha knows to literally pause the assembly line until the promise resolves. For example, if you use an async before each hook to deploy fresh contracts, you ensure that every single test starts from a perfectly clean slate. No contamination bleeding over between tests, and again, no ghosts in the machine. A really critical point to remember here is about timeouts. You always want to use async on your hook functions and await the work inside them. But keep in mind, Mocha's default timeout is usually hovering around 2,000 milliseconds. Honestly, that might be way too short for a heavy contract deployment on a test network. So don't be afraid to manually adjust that timeout using this.timeout. It keeps the machine running smoothly so you don't throw a false failure just because it took an extra second to compile.
All right, Section 4, the predictable test pattern.
When we bring all these pieces together, it forms a master sequence. This 3-step chronological discipline is exactly the kind of deterministic, foundational blueprint we emphasize across Forge College's developer courses. Step 1, submit the transaction. Step 2, await the receipt. Step 3, assert the state. If you stick to this simple 1-2-3 rhythm, you completely turn non-deterministic timing into explicit sequencing. And boom, the flaky test mystery is eliminated.
Here's what Step 3 actually looks like in practice. Only after the ctx.wait has been called do you query the contract state, like, say, fetching the balance here, and perform your assertions. Because you waited for the receipt, you know for a fact you're looking at the finalized data, no guessing.
Let's roll into Section 5, Handling Expected Reverts.
Look, a perfectly engineered machine also needs to safely handle explosions on the assembly line, right? Sometimes you actually want your smart contract to fail, like if someone tries to mint way more tokens than they're allowed to. Instead of leaving a rejected promise unhandled and just letting it crash your test runner, use explicit chime matchers. For instance, using await expect followed by your contract operation .to be.reverted_with ensures Mocha waits for the operation to revert exactly as planned.
This brings us to a golden rule for Web3 testing. Explicit matchers are always greater than implicit assumptions. This explicit pattern guarantees that even when the contract rejects an operation, the test failure remains completely deterministic and totally under your control. It's a controlled demolition rather than a catastrophic factory failure.
And finally, Section 6, your testing blueprint.
Let's lock in the core heuristics of this machine we've built today. These are your ultimate defense against flaky tests. First, await both transaction submission and confirmation using tx.wait. Second, use async on all your Mocha hooks and tests. Third, assert expected failures with explicit matchers like reverted with. And fourth, isolate your state with before each and completely fresh deployments. These practices take all that timing uncertainty and convert it into a highly predictable workflow.
So, I'll leave you with this question. Which flaky test are you going to refactor into a predictable blueprint today? As you gear up for our next lesson on interacting with the blockchain and tests, take this blueprint, open your IDE, and go hunt down those unhandled promise rejections. For more resources, interactive labs, and to dive even deeper into Web3 testing architectures, make sure to visit forge.college. Thanks so much for joining me on this explainer, and happy coding!